Rethinking the role of string theory in physics education, a call for evidence-based teaching. Physics is the cornerstone of humanity's quest to understand the universe. Rooted in observation, testability, and empirical rigor, it provides the foundation for technological innovation and scientific progress. However, the inclusion and persistent advocacy of speculative theories, notably string theory, threaten to undermine the very principles that make physics a credible and impactful science. This challenge extends beyond the theories themselves. It implicates the educators, researchers, and institutions that continue to promote these ideas in academic curricula, shaping the minds of future physicists in unproductive directions. The Threads and Spinons theory not only challenges the validity of string theory, but also offers a superior, evidence-based framework that reaffirms physics' commitment to observable reality. String theory, the rise of speculative physics. String theory emerged in the late 20th century, championed by scientists such as Leonard Susskind, Edward Witten, and Michio Kaku. Its goal was ambitious: to unify the fundamental forces of nature into a single framework. However, achieving this unification required the introduction of up to 11 dimensions, most of which are inaccessible to observation or direct experimentation. While the mathematical elegance of string theory captivated many, it has failed to produce testable predictions or practical applications in decades of research. Despite these shortcomings, string theory remains a dominant topic in many physics classrooms and research programs. This continued advocacy represents a profound misallocation of intellectual and financial resources, diverting attention from tangible scientific inquiries and steering students into the realm of speculative abstraction. The dimensional dilemma. At the heart of the problem lies the speculative nature of multidimensional theories. String theory's reliance on unobservable dimensions transforms it into an exercise of imagination rather than a framework for understanding reality. Physics, as a discipline, should be grounded in the three-dimensional world that we observe and measure. Introducing higher dimensions without empirical evidence is akin to teaching metaphysics or spirituality in a physics class, engaging but ultimately unscientific. If the scientific community accepts multidimensional frameworks like string theory, it opens the door to a slippery slope where any unverifiable concept could claim legitimacy. Should we teach theories of higher spiritual powers in physics classrooms as well? The line between science and speculation must be defended, and physics education must remain rooted in what is observable, testable, and relevant to understanding the real world. Historical context of failed theories. History provides a sobering reminder of the dangers of speculative science. From the phlogiston theory of combustion to the geocentric model of the universe, numerous once popular ideas have been discarded for their lack of empirical grounding. String theory, with its untestable premises and reliance on additional dimensions, risks becoming another such relic. By continuing to teach it in classrooms, we risk embedding a legacy of unscientific thinking in the minds of future physicists. The opportunity cost of string theory. The persistence of string theory in academia comes at a significant cost. Resources, both intellectual and financial, are funneled into a field that has failed to produce empirical evidence or practical outcomes. Research funding, academic programs, and intellectual energy that could be devoted to advancing testable theories are instead wasted on speculative mathematics. This misallocation delays progress in areas such as quantum mechanics, materials science, and cosmology, where practical applications and evidence-based inquiry are desperately needed. The problem with persistent advocacy. The educators and researchers who continue to champion string theory wield considerable influence in academia. Their positions in prestigious institutions allow them to shape curricula, perpetuating the inclusion of speculative frameworks. By framing string theory as an essential component of modern physics, they mislead students and reinforce the false equivalence between mathematical beauty and physical truth. This advocacy creates intellectual echo chambers where alternative viewpoints and competing theories struggle to gain recognition. Innovation is stifled, and the next generation of physicists is trained to prioritize abstraction over observation, hindering the advancement of science. The ethical responsibility of educators. Educators have a profound ethical responsibility to ensure that their teachings align with the principles of scientific inquiry. By advocating for untestable frameworks like string theory, they betray this responsibility, shifting the focus of physics education away from evidence-based exploration and toward indulgence in speculative fantasies. To uphold the integrity of the discipline, educators must prioritize theories grounded in observable reality, equipping students with the tools to address tangible challenges. Threads and Spinons, a grounded alternative. The Threads and Spinons theory offers a powerful and testable alternative to string theory. Rooted in the observable three-dimensional universe, it redefines fundamental phenomena such as light, gravity, and molecular interactions through the interplay of threads and spinons. By emphasizing simplicity, testability, and practicality, it aligns with the core values of physics and advances our understanding of the natural world. This theory demonstrates that complex phenomena can be explained without resorting to additional dimensions or speculative constructs. It reaffirms the sufficiency of three dimensions in describing reality, proving that elegance and empirical validity can coexist. The danger of romanticizing mathematics. One of the primary appeals of string theory lies in its mathematical elegance. However, physics must resist the temptation to equate mathematical beauty with physical truth. While mathematics is a powerful tool for describing nature, it must always be subordinate to observation and experiment. String theory's allure has led many to overlook its lack of empirical grounding, creating a dangerous precedent where untestable ideas are accepted as scientific. A call to action. The inclusion of string theory in physics education must be reevaluated. Its speculative nature, lack of empirical evidence, and untestable premises make it unsuitable for foundational learning. Removing it from the curriculum is not an attack on imagination, it is a defense of science. By focusing on theories like threads and spawns, which respect the boundaries of observable reality, we honor the essence of physics as a discipline. This shift would free up resources for research that addresses real-world problems, foster innovation by breaking intellectual echo chambers, and prepare students to tackle the challenges of the three-dimensional universe with clarity and precision. Conclusion: safeguarding the future of physics. Physics is a tool for understanding nature as it is, not as it is imagined. The persistence of string theory in education risks turning science into speculative philosophy. By refocusing on evidence-based frameworks like threads and spinons, we can restore the integrity of physics, inspire meaningful discovery, and ensure that the next generation of physicists is prepared to advance humanity's understanding of the universe. It is time for the scientific community to hold itself accountable. Physics classrooms must remain spaces for critical thinking, grounded inquiry, and the pursuit of observable truth. Only then can we fully harness the power of science to illuminate the mysteries of our world.